Hello, good morning, everyone. Hello, yeah. So, yesterday we had come to this position of center of mass for continuous mass system. This was the last topic that we discussed yesterday. We shall continue from there itself. Yeah. So the idea was to break down this continuous mass system into smaller elements, right? Into smaller elements like a rod or a linear mass distribution, right? A linear mass distribution like a rod can be broken down into smaller elements like point masses. Right. Similarly, a surface mass distribution like a disk can be broken down into smaller linear elements. And volumetric mass distribution like a solid sphere can be broken down into surface elements like a shell. So these are the types of distributions that we are going to look at, and these are the types of elements that we're going to break it down into. All right. So let's take an example of a rod first. Right. We know that the center of mass of a rod, the center of mass of the rod of a uniform rod will be at the center. Right. Center of mass of the rod will be at the center. So let's have a look at it. Also, if you are here for the first time, I request you to please subscribe to this channel, IITP Classroom. We are doing this free basics series every day. At 11 a.m., wherein we teach the basic concepts of the entire subject for free, right? So please help us propagate. All right. So I want to find out the position of center of mass of a uniform rod, right? So first I'm talking about a linear mass distribution. Right? So in that I'm talking about a uniform rod. uniform rod. So we do know that the center of mass for a uniform rod will be at its center. But I just want to calculate it. Let's see if we can do that using the method of continuous mass distribution. Let's see if we can do that. Right. Now what I'm going to do is I'm going to consider the rod is placed on the x-axis. Alright, the rod is placed on the x-axis, and this is the y-axis. Alright, the rod is placed on the x-axis, and this is the y-axis. Now, to calculate the center of mass of the rod, which is a linear mass distribution, first of all, understand what is a linear mass distribution. Linear mass density which is represented by lambda or mu, it is basically mass per unit length. All right. So this can be written as complete mass by unit length. If it is a constant, then we can write it as complete mass per unit length. Or if it is a variable, then we have to take small elements and then write it as dm by dl. All right. Anyway, I can write the mass dm of a dl length as lambda into dl. Okay. So that is how we can write it. Now for a uniform rod, lambda is going to be a constant. But now since I want to break it down into small point masses, what I'll have to do is I'll have to choose an element which is from this end, let's say at a distance x, there is a small element of thickness dx. All right. So this dx element, this dx length element, let's say the mass of this dx length element is dm. So the element I know of, now I know of what is the element here. All right. Now we know what is the element. So if the element is dm, elemental mass is dm, I can write this dm as lambda into dl. Right? This elemental mass dm, I can write it as lambda into dl. Now, this entire rod is along the x-axis. So obviously the center of mass, the position of the center of mass, xcm, will be along the x-axis only. The center of mass will be along the x-axis only, because there is no mass placed on the y-axis. So the center of mass will only be along the x-axis. So I can write x coordinate of the center of mass as integral dm into x upon integral dm. Right? Integral dm into x upon integral dm. All right. So here the length element is dx. Sorry, the base of dx. Okay. Now I can write dm. Dm I can write it as integral. This is lambda dm. Dm can be written as integral lambda dx. Sorry. into the x coordinate of the center of mass of this upon integral lambda dx. This is how it comes out to be. This is how it comes out to be. Right. Lambda into dx is dm, right? So this is how you get it. Now, if lambda is constant, if lambda is a constant, we can take it out of the integration sign. We can take it out of the integration sign. This is how we'll get. So lambda gets cancelled and it is integral x dx upon integral dx. So integral x dx, integrating it from 0 to L. So x dx will be x square by 2, limit 0 to L, and integral dx will be x 0 to L. So if you substitute the limits, you get the center of mass to be at a distance of L by 2, at a distance of L by 2 from the end here. So this were the limits. This is x equal to 0 and this is x equal to L. So we have x equal to L by 2. We knew this. We knew that the center of mass of a uniform rod will lie at its center. We knew this. But I just wanted to explain the method, how to solve such questions. So obviously, you will not be asked to find the center of mass of a uniform rod. You will be asked to, let's say, find the center of mass of a non-uniform rod. Right? Non-uniform rod. Now, what is a non-uniform rod? A non-uniform rod is the one in which the linear mass density is variable. Right? It is not constant. All right. So, like here, we could take lambda out of the integration sign because it was a constant. But when it is a variable, we cannot take it out of the integration sign because all the variables need to be integrated. Okay. So let's try and solve one such question where the lambda is variable. We have a non-uniform rod. That we have a non-uniform rod. Let's try and solve such question. Let's say the lambda is given as a plus bx. This is a variable. A simple variation, not a very difficult variation. All right. So the entire process is going to be the same. Only the integration part is going to be different. So I can take this entire diagram here itself. because it is the same, right? So I can still go on and say the same things about the center of mass, that it is going to lie on the x-axis. So the x coordinate of the center of mass can be written as dm into x upon integral dm. So integral lambda into dx x upon integral lambda into dx. Now I cannot cancel out lambda here because lambda is a variable. Also, it is a variable in x. So it needs to be integrated over x. Right? It needs to be integrated over x. So what I can do is I can write this as, I can substitute the value of lambda here. So I can write this as a plus bx into x dx upon integral a plus bx into dx. That is it. Now it's a simple integration. Right? Integrating it from 0 to L. Integrating it from 0 to L. Right? If you look at this, this will be AL plus BL square by 2. Oh, sorry. So this is what you will get, the integration part. All right. Now, depending on the values of A and A, B, and everything, we can we can check where will exactly lie. All right. So that is about the non-uniform rod. So like that, this is one such example. All right. This is not the only type of variation that we can have in linear mass distribution. This is one such example. Right. One such example. We can have any type of variation possible. Right. We can have any type of variation which is possible. This is just one such example. Now, I could have something like ax square plus bx cube or whatever ln of a b, ln of ax upon b. So I can have any form of variation. But the major point is the process remains the same. All right, the process remains the same. So that is exactly how we will continue doing it. All right. So, All right. Let's try and calculate the position of center of mass for, let's say, circular arc. What will the position of center of mass for a circular arc? So I'm trying to find this position of center of mass for a circular arc. All right. So the arc is, let's say, symmetric about this point. So this is where the arc is, right? This is the arc. Again, this is the arc. So the mass is lying on this arc itself. All right. And this is the line joining the center to the end points of the arc. All right. So this is what the entire situation is going to be. Right. First of all, if I see the entire mass is lying on the in this quadrant, like first and second quadrant, but it is symmetric about the y-axis. The entire mass is symmetric about the y-axis. If you can look at this, the entire mass is symmetric about the y-axis. Right. So if it is symmetric about the y-axis, can we say that whatever the contribution of mass is to take the center of mass, to shift the center of mass towards the positive x-axis, equal contribution is there to take the center of mass towards negative x-axis? Am I making sense? What I'm trying to say here is, जितना भी मास पॉजिटिव एक्स एक्सिस में है वो सेंटर ऑफ मास को उतना पॉजिटिव एक्स एक्सिस में ले जाने की कोशिश करेगा. जितना भी मास नेगेटिव एक्स एक्सिस में है वो सेंटर ऑफ मास को नेगेटिव एक्स एक्सिस तरफ लेके जाने की कोशिश करेगा. Now, as we can see, the mass distribution is symmetric about the y-axis. Since the mass distribution is symmetric about the y-axis, I can say the center of mass, will remain on the y-axis just because there is an equal there's an equal weightage. There's an equal weightage of masses on both the sides of the y-axis. It does an equal weightage. All right. So since there is an equal weightage, that is why we can say both on both the sides, the mass will be distributed equally, and that is why the center of mass is going to remain on the y-axis itself. Right. That is a point to be noted as well. That the center of mass will always remain on the. It will always be on the axis of symmetry. Will always be on the axis of symmetry. Right. And in cases where there are multiple axes of symmetry, then the center of mass will lie at the intersection of those axes. So if at all we have such a situation wherein we have multiple axes of symmetry, like for a ring, any diameter is for a uniform ring, any diameter is the axis of symmetry. Right, any diameter is the axis of symmetry. So the intersection of any two diameters will be at the center, and that is going to be the center of mass for a ring. So for a circular arc, we do not have more than one axis of symmetry. It is only the y-axis here, which is basically the angle bisector. Yeah, this is the angle bisector. So let's say that this angle is theta, or theta by 2, as I'm going to write the entire angle as theta. All right. So how do we proceed with this? So proceeding will be, I'll take some mass here. I'll choose some mass. Yeah. So I've chosen this mass element. I've chosen the mass element which lies between these two lines. Right. So what I've chosen is at an angle phi from here and thickness d phi. I've chosen some mass element here, which is dm. All right. So this is dm mass. Now, integrating such dm masses, I will get the entire ring. Okay. So just for the calculations to be easier, I will show that this is the x coordinate of this, and this is the y coordinate. Correct. And this is the radius r of the arc. All right. So what I'm going to say is, since y-axis is the axis of symmetry, y-axis is the axis of symmetry. X coordinate of the center of mass will be 0 because symmetric mass distribution है उसके about. तो जो भी center of mass रहेगा axis of symmetry पे ही रहेगा. ठीक है? So that is why if the center of mass is on the y-axis itself, the x coordinate of the center of mass will be 0. X coordinate of the center of mass will be 0. Right. Now what I need to do is I need to find the y coordinate of the center. The y coordinate of the center of mass is integral dm into y upon integral dm. So what is integral dm? Integral dm will be equal to lambda into dl into y coordinate. Y coordinate will be r cos phi upon integral dm, which is lambda into dl. Right. Now what is dl here? Dm will be equal to lambda into dl. What is dl here? This length is dl. So I can write this as this length dl as r into d phi. Lambda into r into d phi. Alright. So, and since it is a uniform circular arc, then I can cancel lambda because it is constant. Otherwise, I could not have. So, integral dl we can write as r into d phi into cos phi upon integral r into d phi. Right. So this is, I can cancel 1r. Again, it is constant. That is why. So what I'm left with is r into integral cos phi d phi upon integral d phi. Now we need to substitute the values of phi. So phi, as you can see, this is the angle phi, which is making with the y-axis, right? So if it starts from 0, this is where it starts from, and here it goes till theta by 2 plus theta by 2. So it must start from this point. So this point is phi equal to minus theta by 2. So phi goes from minus theta by 2 to plus theta by 2. Right, minus theta by 2 to plus theta by 2. All right. Integral cos phi is sin phi. Integral cos phi is sin phi. So sin phi limits going from minus theta by 2 to plus theta by 2. Upon divided by d phi. Integral d phi is phi. Again, limits going from minus theta by 2 to plus theta by 2. So I can write this as r. This will be 2r sin theta by 2 upon theta. This will be the position of center of mass for a uniform circular arc. चलो. So if this were a semicircular arc, if it were a semicircular arc, for a semicircular arc, the coordinate y coordinate of the center of mass be equal to 2r sine of pi by 2 by pi. What is sine pi by 2? That is 1. So you will get it as 2r by pi. ठीक है? This is for a semicircular arc. ये रिजल्ट आपको याद रखना पड़ेगा. ये रिजल्ट आपको याद रखना पड़ेगा बिकॉज दिस इज अ डायरेक्ट, मतलब ये डायरेक्ट क्वेश्चन हम लोग को आता है सेमी सर्कुलर आर्क के लिए. तो आप मतलब यू कैन रिमेंबर फॉर a circular arc subtending angle theta, that is better. That is better. You can remember for circular arc subtending angle theta, that is better. And then using that you can find the position of center of mass for a semicircular arc, because that is one of the cases of a semicircular arc, right? So we can do that. All right. So this is the condition here for linear mass distribution. Similarly, we have surface mass distributions and volumetric mass distributions as well. Okay. Let's now try and calculate the position of center of mass for, like we have done for linear mass distributions. Let's do it for surface mass distribution. Let's do it for surface mass distribution. Now for surface mass distributions, I can say surface mass density is sigma, that is the mass per unit area. Sigma is the mass per unit area, which can be written as dm by dA. Right. So I'll write this as small because every time I use small m for mass. So I can write dm is equal to sigma into dA. Then if it is a variable, it will stay inside the integration sign. If it is a constant, it will come out of the integration sign. So that is about it. That is the only difference that is going to happen here. So dm is equal to sigma into dA. All right. So let's try and find the positions of center of mass for surface mass distribution. So we have different surface mass distributions. Right? We could have a triangle. We could have that is a triangular plate. We could have a rectangular plate. We could have a disk, right, which is a circular plate. So basically, any surface or any plate of any arbitrary shape can be considered to be as a surface mass distribution. Also, also some uh, some closed figures which are hollow inside will be considered as surface mass distributions. So a spherical shell means it is hollow from inside. A spherical shell can be considered a spherical shell can be considered to be a hollow can be considered to be a surface mass distribution, right? And yeah, hollow cone also works in that case. Hollow cone also works in that case. Then yeah, there are a lot of mass elements. There are a lot of mass elements which will work as surface mass distributions, right? So we can derive all of that, but I'll just give you the brief idea of how do we do that, and then we can continue with the discussion ahead. Right? Just a moment. Just a moment. Yeah. So what I'm going to do is I'm going to write the positions of center of mass for different objects which are considered under the surface mass distributions. You can look up the derivations everywhere. Right? They are given in all the standard textbooks. Correct. So let me just make a list of all the surface mass distributions that we're going to talk about, that we're going to discuss about. Correct. So the first one that you should remember in this is like the circular arc that we did, right? The circular arc that we did, similar to that, but the entire mass is distributed over this plane. So I'm going to call it a sector of a disk. I'm going to call it a sector of a disk. Right. Now, what is a sector of a disk? It's like circular arc, but full. So imagine like a pizza slice. So a pizza slice is something which can be classified as a sector of a disk. All right. So this. So the entire mass is distributed here. Entire mass is distributed here. So this is a sector of a disk. There is some mass here. Which is uniformly distributed. All right. The sector of a disk, I can say this is the y-axis, and the entire mass is distributed uniformly on this y-axis. About this y-axis, I'm sorry, and this is the x-axis. All right. So the center of mass will be somewhere here on the y-axis itself. This is where the position of center of mass is going to be, right? And let's say this is the y coordinate of the position of center of mass, and the angle that it subtends, the entire angle that it subtends is theta. So the y coordinate of the center of mass for a sector of a disk can be written as 4r sine theta by 2 by 3 theta. 4r sine theta by 2 by 3 theta. That is the y coordinate of the center of mass. That is the y coordinate of the center of mass. 4r sine theta by 2 by 3 theta. That is the y coordinate of the center of mass. All right. So this implies that for a semicircular disk, for a semicircular disk. So what will be a semicircular disk? This is going to be a semicircular disk. This is going to be a semicircular disk. So let's say this is the x-axis. And this is the y-axis. Right. And the center of mass is going to lie on this axis itself. So this is where the center of mass is going to be. So we can find what is the position of the center of mass. Let's call this as y. So y will be, since theta is pi here, you will get it as 4r sine of pi by 2, which is 1 upon 3 pi. So this is a standard result that you must remember. Right? This is a standard result that you must remember. It is better if you remember for a sector of a disk, right? Here the mass distribution is uniform, as I have already mentioned. This is for a uniform mass distribution only. If the mass distribution is non-uniform, then you will have to integrate it, right? And then you might get it at some other position, right? So this is only for uniform distribution of masses. Okay, so that is for a sector of a disk. Next, we can have a hollow hemisphere, which we can call it as a hemispherical shell. Right. It does not make sense to take a complete hemispherical shell because obviously the center of mass for an entire spherical shell will be at its center. So that is why we are taking a hemispherical shell. So this is a hemispherical shell. So this is what a hemispherical shell is. The mass is distributed on the surface now. The mass is only on the surface. It is not inside. All right. It is hollow. You can see this is hollow. Okay. So let's say this is the center and this is the x-axis. This is the y-axis. So again, I can say the entire mass is uniform about the y-axis. So the center of mass must be at some position on the y-axis itself. So this is where the center of mass will be. You can also you can also tell this from intuition. Even if you do not know the exact position of center of mass, you can tell this from intuition that the center of mass is going to lie somewhere on the y-axis itself. So the y coordinate of the center of mass here for the hemispherical shell is r by 2. It is r by 2. Right. How do we do it? You can calculate the center of mass for this by taking infinitely many rings. All right. You can start as you can consider a ring at an angle theta with y-axis, right? At an angle theta with the y-axis, you can consider a ring, and you can go on adding such rings on top of each other. And you can form this hemisphere. Correct. So what we can do is now we can also write for uh, let's say a hollow cone. That will also make a good. If you remember this, it will make a good impact on your studies. So let's consider for a hollow cone, right circular hollow cone. Okay. So if I have a cone, So in the cone as well, you can see the vertical height is going to be your axis of symmetry. Vertical height is going to be your axis of symmetry, right? So if this is the center, let's say this is the axis. The y-axis. This y-axis is going to be the axis of symmetry, right? Y-axis is going to be the axis of symmetry. So you can say this is a cone, right? Right. The center of mass is going to be somewhere here. Right. This is going to be the y coordinate of the center of mass. So for a hollow cone, we can again check what is the y coordinate of the center of mass. Right. How do we do it? We actually find it using rings and everything. Okay. So what do we do? We this is again, this is a set. This is a surface mass distribution. So what I can do is I can break it down into rings. Right. I can break it down into rings. And if I break it down into rings, I can calculate the position of the center of mass. I can calculate the position of center of mass. Right. And it comes out to be like a triangle. So the position of the center of mass here is similar to a triangular plate, which is at a height of h by 3 from the base, which is like a centroid of a triangular plate. So if I were to have a triangular plate, then the center of mass for that triangular plate will also be at the same position as this one. So this is for a hollow cone. So we can have a lot of other elements as well. The idea is to break them down into smaller elements and then integrate it for a larger mass. Okay, so this is the idea behind doing all of these center of masses. So please remember these. All right, please remember these standard results so that you save time in your exam. Okay, the next part of this will be done on the next on the coming Monday, right? We will have another lecture tomorrow, but of different subject. So that is it from my side. Thank you for joining in. Have a good day. Take care, everyone.